anyway, so the topic sort of says itself, and I'll explain a little further on. But first of all, okay, if you're going to be a VFS hacker, we're going to talk about the VFS mid-layer. And what the heck is this? Okay? Well, file systems in OpenBSD and actually in any modern Unix are not implemented to write directly to disk. They used to be in the bad old dark ages, in the original versions of Berkeley. You had things called inodes. Inodes were just disk blocks. They stayed on disks. Somebody had the bright idea that they liked several different file systems, and rather than each file system having to re-implement the way to get to the disk with the inode, they implemented what was called the VFS layer. And the VFS layer, so the virtual file system layer in the kernel, it consists of a way to put things together such that you can add a file system to the kernel without really knowing the gory details of how the kernel puts crap on disk. You don't have to know how different WD is from SD, from CD-ROM, from anything else like that. So the VFS layer is nice to have. It provides an abstraction of a disk in the form of a vnode. You get a vnode. This represents an object on the disk. Could be a device, could be a directory, could be anything like that. And a vnode will have operations you can do on it, and things are hung off that to do things like open and close, read blocks, write blocks, good things like that. Generally, they make writing general file systems a lot easier because you can write a file system to talk to the VFS layer, and if stuff changes underneath you, you don't have to care about it. Yeah.
Theoretically.
Theoretically. The other very, very important thing is they are used to implement some very important optimizations that are key for the performance of any Unix system, OpenBSD or anything. And that's the buffer cache, the name cache, and the inode cache. Okay, and what are those things? Well, the buffer cache is simply that. It's a cache for buffers. Objects, blocks read off disk, a buffer, are cached in memory. Okay? This is because you don't want to constantly go to disk. It's slow. Okay? Even when your disk has gigantic caches of RAM, and people say, but what about SSD? Yeah, it's still on a bus. It's not your memory subsystem. Okay? No matter how fast they make it, okay, your memory subsystem with your CPU cache is always going to be an order of magnitude faster than anything they hang off of a SATA bus. Okay? Or SAS, or SCSI, or whatever. Okay? So the buffer cache just basically caches blocks read off disk. Boofs. Okay? The name cache is something different. The name cache is, well, if I have a file named Fred, where the hell is that file and are pieces of that file in memory? Okay? So the name cache is a way to find bits of a file that you already have. The inode cache similarly says, if I have this disk block, what file does it belong to? Okay? It interacts very heavily with the virtual memory system, with UVM and OpenBSD. Okay? And lots of things kind of depend and interdepend on this, as we'll see. So, onward and upward. When you change the VFS mid layer, or you change how it behaves in any way, okay, they affect things. They affect the file systems in the layer above you, okay? It affects the I/O system below you. And there's this thing called NFS, which is this gigantic layering violation written by Sun in the 80s, which kind of pulls packets off the network, mangles them, and shoves them onto disk somewhere else and pretends like it's a disk locally. It has this unfortunate property that it's used in very sick and twisted ways by our build system, and what that means is Theo runs it all the time. Which means if you break it, your ass is grass. Okay? Because we can't build. Okay? And we can't continue building the system, and we can't do quality checks, and we don't know what the hell's going on. So, as I mentioned, NFS kind of sticks its fingers into everything. And when you get NFS into the mix, things really get weird. Okay? Because NFS kind of does some horrible abuse of the VFS mid-layer in order to do its job. Okay? NFS will take buffers that should be dirty but say, well, no, pretend that's not. Okay? There's something even worse called soft dep. SoftDep is enough to just make your toes curl, but we won't talk too much about that here. The main point to realize here is when you change this or even change how it behaves, what happens is you start to expose everyone else's bugs. Yeah, you'll introduce your own share of them in any changes you make, but the scary part is you'll think, I can change this to do these particular things. What'll end up happening is you'll do that exactly right, and it'll conform to the vnode interface, but then you find out that, well, the file systems don't quite do that way, or more importantly, this file system has a bug that you've now exposed by doing that. So, for instance, when NFS happens to release the reference count on a vnode 3 times every time it should release it once, random weird things start happening, and they start happening quickly. And changes you didn't intend don't happen. Or better, when NFS version 2 screws it up, and the only thing anybody sane in this room ever uses is NFS version 3. The only people who use NFS version 2 are people using the AMD Automounter. Oh wait, that's Theo. And you start to introduce bugs in this, and things go south really, really fast. And so again, APIs, very dangerous. You go first. So back to why you should not be a file system hacker and you should not be a memory subsystem hacker. Go hack the network stack, okay? If you're a network hacker, you get to do fun stuff. You get to write code that's mostly your own. You get to implement big, complex ideas. You get to speed up the network hacking the kernel, speed up your firewall hacking PF. You get to pick up and replace nasty daemons that everybody hates in user land. You get to, write stuff to stop spam. I've done that. It's fun. People love you. They adore you. They worship the ground you walk on. Everybody loves you, and you are amazing, okay? When you break something, well, only your little piece of the network or the internet becomes unreliable. God, the internet's unreliable. I've never heard of that. So, but your systems tend to keep working, and nothing horrible happens that, brings the world to an end. And so it's really, really fun to hack in the network. You get to implement big ideas, you get to replace big things or change big things, and if you break it a little bit for a little while, well, okay, you only broke that little piece of the system. Okay? Oh, it's different in file system and VFS land. Okay? File system and VFS cache hackers, well, they get to expose bugs throughout the mid-layer, especially NFS, especially SoftDep, especially every file system. Code written back in the 80s at Berkeley before SMP was an issue. Code written by random people, hacked on stuff, men and women. Code changed and mangled so that they could publish a paper at Usenix and get a DARPA grant and then abandon this code never to be seen again. Nobody runs it because it was a bad idea in the first place, but it got the money from the US military. All sorts of things like this that are sprinkled through Unix. Okay? You go and do something which you believe will have this effect and it doesn't. It's pretty straightforward to realize when you're hacking in the network layer that if you reduce the latency and increase the packet throughput, stuff goes faster. Simple assumptions like that don't work in the file system layer, and they don't work in the buffer cache layer. When your changes don't work, it's not like, oh, geez, the spam deferral system stopped working, or PF got a little bit slower, or, redirect rules with scrub don't work until you commit a diff. No, when changes don't work, you get yelled at by everybody, okay? People lose their porn, okay? File systems get corrupted, okay? Really, really, really bad shit happens, okay? The system becomes completely unstable. What's worse is because the bugs are sometimes up in mid layers and down below, you're dealing with queuing, with buffers. Oftentimes the bugs don't show up very often. They're non-deterministic bugs. They only show up on certain small systems, or systems in certain configurations, okay? Or systems with certain amounts of memory. And they're very, very, very difficult to reproduce, okay?
They actually happen when you're hiking.
And yes, they generally happen when you do a commit, wait around for a week, think everything is good, and you go to the mountains. That's a sure sign that something horrible is going to happen with the mid-layer. Definitely happened after C2K9. All of us went out to the bush, and meanwhile, the shit totally hit the fan. When your changes do work, they're generally invisible. Oftentimes, the only people notice, yeah, sure, we're all a bunch of nerds, and we all tend to pay attention more to our computer than the average, mouth-breathing knuckle dragger running OSUX or Windows. But generally speaking, only the worst of us tend to run builds in a loop and time them. Okay? And this kind of work you do in this layer is the kind of stuff where, oh look, build time decreased by 5%. Most people in the room wouldn't notice. You know, the rest of us go, yeah, that's awesome. But people don't tend to notice. People don't tend to give you fame and adoration, and they don't tend to give you money to go work for companies and do things when you hack on this sort of stuff. So, what kind of people work in the VFS layer? Well, they tend to kind of be a people with an abiding interest in pain. Okay? Or they tend to be victims of the same, because people with an abiding interest in pain usually like to suck people in to share that pain. Okay? So people kind of tend to avoid them because they're often dark and bitter, they smoke a lot, or because, God forbid, they might ask them to test one of their diffs. Okay, and I might lose my porn. So, you know, some of you may know people who fit this description. Art Grabowski. And he's one of the worst offenders. But so, when you see this, I have something to show you what it's like to learn about the VM system and the complexity of it, and what it's like to be introduced. So anyway, given that this is this amount of suffering and will actually suck years out of your life, why do we do this? And why do we look at this? And why do we want to do things on particularly the buffer cache? Well, as you know, doing direct I/O to disk sucks. Okay? Nothing will possibly ever be as fast as your memory bandwidth. It's nice to use memory. Unused memory is much faster than disks. So, as I said, when I was young and had a mullet, back in the 80s, I had to buy really, really, really fucking expensive computers to use Linux, to use Unix, to use, you know, BSD 386 or nascent versions of Linux. You know, to be able to get, God forbid, you know, I had to scrape the bank account to get a whopping 12 megabytes of RAM, at which point I counted myself to be incredibly fortunate. Nowadays, to get a machine with 16 megabytes of RAM, I have to emulate it in parallels on an OSUX machine, and it consumes 768 megabytes of memory resident to emulate a 32 megabyte i386 machine. But virtualization's awesome, you know. Having said that, KDE, GNOME, Mozilla, Apple, all the purveyors of fine bloatware that we have these days that drive computer sales have made it so that it's actually cheaper to buy a computer with a healthy amount of RAM than it is to get drunk in Stockholm. Okay? So you can get computers with lots and lots and lots of RAM very, very inexpensively these days compared to the way you used to. But you don't want to get in the way of using memory for working set. That's the key thing. And that's a key difference between what we've been looking at than what a lot of other operating systems do these days. Okay? It's all great to cache I/O to disks, but when it really comes down to it, it's just I/O to disks, and eventually you're going to wait. If you start sending working set memory to paging space in favor of I/O to disks, this is always wrong. Guys, this sucks. So, what about the buffer cache in OpenBSD? Well, it actually used to be mapped directly from kernel memory, all of it. So it's basically the equivalent to a great big malloc in the kernel. It was all mapped in KVA, the kernel virtual address space. And you have to understand the kernel virtual address space is limited on most architectures. Okay? Most of the time it's limited because the virtual memory handler can't handle mapping two different sets of stuff for kernel versus user space. You have to say, this piece of the virtual address space is reserved for the kernel, this piece is reserved for user land and everything else. You don't want to map the whole virtual address space for the kernel, or you want to run a user land program? Well, no, you don't get to have any memory. The kernel has it all. Some architectures don't have this problem. You Spark 64, you can map everything as the MMU handles it. But the first step to having the buffer cache be large, and it used to be mapped straight from kernel memory, that was basically fixed. So if you've ever done config of an OpenBSD kernel, you'd notice there's a parameter called cache%, cache PCT, that you used to be able to change in config, and this would let you change the size of the buffer cache. You could, and by default it was set to around 10% on all of our architectures. only 10% of memory. So if you had 4 gigs of memory and you were piddling around with, you know, regular sane daemons instead of running gigantic bloated shit that a lot of people have to run. But if you're running, you know, sane, you know, HTTP daemons and stuff like that, you'd be fine. And you'd have all this memory sitting there, and gosh, what do you do with it? You know, you could make your IOs that much faster, you're not using it. The amount you have is limited and fixed at 10%. A lot of times this was due to kernel VM space limitations. So the first thing to do was actually make it such that the buffer cache, and remember, it's a cache. Most of what's sitting in there is completely unused. It's only usable when we need to reference it. So the trick is to actually only leave the pages in memory, but only map them into VM space when we need them. Okay, unmap them otherwise. That way it doesn't consume all of kernel memory space in order to have a large buffer cache. This was the VFS biomem.c stuff, and it was used, Art Grabowski in Vienna, with a few of us helping him and torturing him and being tortured by ourselves, worked on this largely at Vienna F2K7 and shortly afterwards, so that we could extend the buffer cache without running out of kernel memory. Okay? It took lots of time and pain to get it in, including some reworking of the buffer cache, and including backing out some incorrect assumptions. Many developers just said, well, if we have a bigger buffer cache, and the buffer cache is this big, we have to change the number of vnodes too. And we'll talk about that in a second here. Well, if the buffer cache is this, well, why do we worry about vnodes? Okay? Well, we'll get there, but now, thanks to the map and unmap change, we actually have a bigger buffer cache. It was done at C2K9. You can now set this via a knob in sysctl in current. It's mostly harmless. It defaults to the same level as before, which is 10%, but you can now move this knob up. So sysctl minus w current.buffcache% equals 90 will now let the buffer cache grow up to 90% of your memory. And it will again fall back down at the lowest level to 10%, the former default. Now, when I say that, previously it used to just reserve 10% of memory. Now it actually is allowed to grow and shrink. Okay? What was involved in that? Well, we had to allow the buffer cache to extend itself to the high water mark. That's adding the sysctl buffcache%. We actually had to go in and chainsaw the page daemon to kick the buffer cache back down when it needs memory, and this is important. Remember what I said, we don't want to evict working set. So just because you decide that currently you're using 2/3 of your memory to cache file system pages, when all of a sudden your HTTP daemon now gets busy and needs to do some work, but it needs memory to do that. Oh, well, do you all of a sudden want to be paging just because you've got a bunch of file system pages in memory? No. What you actually want to do is you want to kick those pages back out, okay, so that you don't have to deal with it and you have that memory available for working set, at least down to a minimal amount. This is very, very different from what a lot of other operating systems do. So, for example, AIX, Solaris, and Linux, by and large, will try to have this floating line, magic bullshit line somewhere in memory where they try to prefer to keep file system pages versus preferring to keep memory pages, which is wonderful in theory but really sucks in practice because people, the kind of monkeys that you buy on contract to write software don't write software that way. Okay? What inevitably happens, and I've seen this on AIX and Solaris machines running crappy software, is that when you hire monkeys in India to write your software, they tend to decide that, oh, disk is slow, therefore I'll use a cache in memory to hide all my IOs. Hey, wait, isn't that what we're doing? Well, but then they do it in userland, and so they do malloc, gigantisch. Read from disk, stick in memory. So this is a read, which you keep in the buffer cache, which they then copy into an allocated hunk of memory, and then when they want to write it out again, they do write, which you then write to the buffer cache, and then copy back out. Can anyone see the problem yet? When you are trying to keep, if you're trying to keep preferentially keep buffer cache pages in memory, what ends up happening is they say, to tune our software best, please allocate 12 gigabytes of I/O cache for TSM. Oh, jeez, did I admit who I've seen this with? And what happens is that TSM will then go read the I/O from disk, which comes into the buffer cache. The buffer cache is then mem-copied into a malloc data area. Oh shit, there's no memory, so swap pages out, so the buffer cache gets pushed back out to disk. Oh, then it has to write it out to disk, so it has to do a write. Well, the write needs the buffer cache, so now we swap the malloc area out again, and then we bring in the buffer cache. So we find ourselves committing swap-aside for no good reason at all. So the fact is people write software in stupid ways that do this. And what it really comes down to is that if the system needs memory to work, let it have it. Okay? We can't change what userland does. Keep a minimal amount to keep the buffer cache functional, and that's that. Okay? So again, the goal is, well, prevent stuff from competing with memory. We actually I did this at C2K9. It was backed out in a gigantic mess that happened after C2K9 due to some UVM commits by some guilty people. But however, we've now been able to bring it in and do a bunch of stability fixes here from Sweden, in Sweden with the hackathon for low memory machines. I've been torturing lots of fake i386 machines and VAXs in very low memory configurations to ensure that this still works stably with the page daemon. And so this now I believe is fairly safe. We're running it everywhere. The interesting thing is, remember, the default is still 10%. If you want to have fun, crank it up to 90. It's relatively safe. And you can watch sys.io. Will show you the number of buffer pages. And as you increase your system activity, you'll notice that kick down, kick down, kick down, until about 10%, where if you're using lots of memory, then your machine will start to swap. But not beforehand. Well, great, you've got a big buffer cache. Can you use it? Well, maybe. And it gets worse, okay? To make use of the buffer cache, you need a vnode. If you don't have a vnode, you can't see the pages. The pages are hung off of a vnode, okay? Well, currently in vnode, in OpenBSD, vnodes are a fixed size table, okay? So you think, you think, well, we could make the buffer cache dynamic. Let's make the vnodes dynamic, right? How hard can this be? Well, here's Kandiru. If you don't know what it is, look it up. The network hackers who have always invade every hackathon, they're rock stars and they're pretty and they have nice hair. And they always say there's dragons in IP input, but dragons kill you quickly. Okay, Kandiru kill you slowly and painfully. Look them up on Google. That's what happens in the Vfs layer. And I'll show you why. You can't just make the vnodes dynamic. Vnode is a static allocation at boot time. Anytime we change it, it exposes bugs, particularly in NFS. And it affects I/O rates. So what really pushes disk to I/O in OpenBSD, other than developers? Who knows? Obviously the syncer, right? Sync runs every 30 seconds, kicks buffers out to disk. Boom, 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 boom. Obviously, if you unmount the file system, well, that's going to flush all the buffers, right? What else kicks buffers out to disk? Do we only write stuff out every 30 seconds? Who knows?
Well, if you end up
You've got an Arliss shirt on.
Yeah.
You're the worst vnode abuser on the planet. My God.
Of course.
Anyway, yeah. So you may know. Anyway, continue.
Well, if you end up not having any vnodes, you push out the ones.
Right, what it actually is vnode recycling. Okay, when you don't have enough vnodes because you have this small number, you recycle vnodes. When you recycle vnodes, oh, I'm going to steal this vnode and use it for something else. If it's got buffers hanging off it, then you push all the buffers in the vnode out to disk. So stuff that keeps us from just sitting there and only doing I/O every 30 seconds when the syncer runs is actually vnode pressure. So an unintended consequence of not having very many vnodes is that you push I/O to disk. Hey, wait a minute. So if I have lots of vnodes, what happens? All of a sudden the I/O becomes very bursty. Blap, blap, blap. Every second when the syncer runs. This isn't always what you want. You thought you were going to make the system faster, and all of a sudden performance sucks. Okay? So there's horrible, horrible things happening here. Well, still, let's say we go and we fiddle and we add a mechanism to kick the vnodes out. Well, let's make vnodes dynamic. Well, it's not quite that easy. Currently, they're reused in a horrible way with a name cache. Welcome to hell, ++ NC VPID. And you have to really read the name cache code to understand my pain here. But what happens is the name cache code keeps pointers to a vnode. It's just an address, right? Okay, well the vnode gets recycled and used for something else. The name cache still has that pointer. Well, so what they did is they introduced this horrific hack, which is every time they reuse a vnode, they increment a counter. And note the welcome, so that would be welcome to hell, ++ NC VPID. That's just a global counter. And then when you look up something in the name cache, what you do is you check, when you add something to the name cache, you save the counter that was present in the vnode, and then when you look up an entry in the vnode, an entry in the name cache, you get a vnode back, you know what ID it had when you added it to the name cache. If the ID is different, you don't touch it. You just close your eyes, you pretend it was like a week in prison with a fat guy in Stockholm, and you just, that never happened, I never saw that. With the requisite thing that if the ID counter wraps, you reset it and goes negative, you reset it back to 0 and increment it again. That's the welcome to purgatory, NCVPID++. If it's less than 0, set it to 0, increment it, and go back to hell. So, as you can imagine, making something dynamic, when the whole cache system has its fingers through this, keeping references and counters everywhere, it's horrible. The only place that matters in the system that does this is the name cache. Well, Arla does it as well, but we won't go there yet. If the VPID in the vnode changes, from the VPID we remember the name cache, we keep going. So this is awful. More or less, in order to make any progress in this, we have to get rid of this hideous design. So, the problem is, when you do this, you get rid of this hideous design, you get vnode reuse everywhere, okay? And the kernel is too stable, okay? We need more panics. We need more panics faster, okay? When you don't have the panics, it takes forever to find this stuff. Because somebody does something horrible by not keeping a lock on a vnode, or not incrementing a counter or checking it, and the bug happens minutes or hours later in the kernel when something is flushed or recycled. Okay? Use after free is deadly in file systems. This makes you lose your porn. Okay? What? Boo. Boo, yes. Losing your porn is bad. So, part of, after problems with some of this stuff at C2K9, a lot of work has been done by various developers, Theo, Ariane, stuff like that, people like that, to implement faster page recycling and some methods to ensure that we can turn knobs when we're testing such that we actually kick pages through the system faster and catch these use after free bugs quicker. Okay? And this becomes a never-ending cycle of testing to get the smallest of these changes in there. So it's difficult to move forward in these things. So, part of what we've recently done, this was done at C2K9 and it was recently committed, we fixed the above horror. We actually made vnode recycling. When a vnode is recycling, it always called the function cache purge. Cache purge just incremented the VPID before. Now it actually clears the name cache entries. And so just remove the entries from the name cache when you recycle the vnode. This makes sense. That was rather difficult before because the name cache was a global hash indexed with a name and an LRU. So if you just had a vnode, you couldn't figure out where the name cache entry was to free it. Well, this is retarded. We get rid of the globally sized static hash table. We then allocate and free the name cache entries from pool, but we make the name cache actually a red-black tree hanging off each vnode. So what we can actually do is we can look up the name, find an entry, and when we have the vnode, we can free them easily. Okay? We actually purge the name cache entry and it was put in. It's now that we have a dynamic name cache, that's in current, we're now in a position where we actually can make an actual dynamic vnode implementation. So we can actually allow vnodes to grow and shrink rather than have them static. I have a diff that does that. It appears not to harm anything. I haven't committed it yet. I'm too afraid. I might one day go as high as 5, but I'm really not sure what that would do to you. So
It's just 3 lines of code.
it's only 3 lines of code, yes. It's a little more than that. The main reason I'm still scared of it is right now it still uses a free list. If I get rid of the free list and just free them immediately, it exposes bugs everywhere in the file system layer. So I know that the only thing that's helping us right now is the fact that that free list still has some delay in how fast things are recycled. And before we can, reliably go to something like this, we have to spend some time beating through all these nasty little use after free bugs over and over through the file system, and particularly in the NFS layer. Hi, Thib!
You got that wrong. The kernel has no bugs. Theo said so.
Yeah, we know the kernel has no bugs. The kernel is too reliable, that's the problem. So, what's the future? Well, future we have several things. A few diffs that I've tossed about with DLG and other things. A little bit of I/O pacing, maybe making sure we have a way to not let one process completely hog the I/O path. That is semi-related. The key thing, again, dynamic vnodes, along with dynamic buffer cache and dynamic name cache. We're getting closer to that now. But again, I don't think we can get as far as the dynamic vnodes without a lot of work testing and getting through some of the nasty use after free bugs in the file system layers. Coherency. This is another thing about the buffer cache. Now people ask, do we have a unified VM system? NetBSD shitheads. I always like to say, but OpenBSD, you don't have a unified buffer cache. Ask them, what's a unified buffer cache? No, not say that you have UBC. Ask them if they know what the fuck it means. Most of them won't know. Well, maybe NetBSD users will, but that's because NetBSD users are just their developers. There's no real users. But most of their developers won't know. BSDT, sorry, I should say.
BSD underscore.
BSD underscore T. Basically, what coherency means is that if you mmap a file, okay, and then you open the file, and you make changes, do you say the same stuff? Okay? And right now in OpenBSD, that's not true. Okay? And there are no guarantees that that's true in POSIX, but lots of other systems do it. Okay? And where they have a coherent buffer cache, that means that changes you make when you map a file into the actual VM pages also appear when you do reads and writes. Okay? Art is working on that. It's another one of these giant diffs that will be intrusive and probably take forever to get in. If he actually stays awake long enough to test it and stabilize it without going completely emo and freaking out when it explodes the first 10 times he tries to put it in the tree, we actually might get there. I've seen versions of this diff that sort of work, but they are not ready yet. The other thing that we'd like to do in this area, and we've talked about a lot, is page flipping for stupid devices. A lot of times people worry about disk drivers and the like that are not 32-bit clean on 64-bit machines. What you end up having a problem with here is that you want to do I/O to the device, and the buffer you want to do I/O to the device from is up there above 4 gigabytes of memory. Okay? But the device can only address 32 bits of memory. So then what you normally have to do, and a lot of people do, is they implement bounce buffers in the device driver, and you have to bounce everything through it, and it's a pain, there's lots of copying. What we'd like to look at trying to do is let the buffer cache and the virtual memory system understand that this device is stupid. It can't address all of memory. So therefore, when you're mapping pages for it, map pages when you talk to it into the range that it can speak. But if you don't have to write them, you can stuff them up into high memory. And when you need to write them, particularly if it's a file system buffer, just trade with one in the right range. Okay? It's simple to trade. Okay? And it's still an idea, but it's a promising one. But like I said, we need some stability and extensibility before we can get this far. Can you help? Yes. Test the diffs you see posted. The biggest, and this is very, very difficult. It is extremely hard for any one of us to have enough hardware and enough weird-ass configurations to test every possible combination of stuff these disks can hit. Okay? It's pretty easy when somebody's changing a network device driver to jam 3 or 4 different Ethernet cards into their machine and tell that their tests have pretty good coverage. It's very, very difficult when it's generic MI code that touches all the horrible places we've talked about. So the biggest thing you can do to help when you see changes that come out in that, test that shit and test it on weird stuff. Test it in your configurations, test it on strange configurations. When you get a panic, get a trace back, get it back to people, get it back to the developers, and talk to them, report decent bugs. Try it. Try it and crank the buffer cache up. I think it's mostly stable, and if you're doing well, it will give you better performance. Okay. Send money. You know the usual places to send money. Okay. And hug a file system hacker. They you know.
Hi, Bob.
Hi, David. Yeah. There's just not enough love to go around. So, and that's about it. Guys, got any questions?
What happened last night between you two?
Him? No, it was you. No, I thought it was Brent's friend that was following us. Brent had a friend last night. Several of them, in fact. And he's just pretty. He attracts attention.
Were they all sailors?
I don't know.